And what number 40 gives us is a process first. Steps 1 to 2 are isovolumetric, because notice the volume doesn't change at all. And then step 2, I guess, is isobaric, because the pressure doesn't change. So they give us the number of moles. We have values on our graph, so we can tell that. And in part A, we want to know how much heat is added to the gas during the first two processes. So I'm first going to consider process 1. And since process 1 is isovolumetric, you can think about it as there's no area under the line there, or the volume of the container is not changing at all. So the big key for this process is that the work done is 0. And what this also means is that your change in internal energy is equal to Q. So all they want us to find right now is what is Q. And let me stop this, sorry, from moving. And in order to go ahead and find Q, I'm going to go ahead and first find my change in internal energy, which is 3/2 times N times R times my change in temperature. Now, in order to get the change in temperature, you have to go ahead and look on your graph. So at T1 on your graph, in order to find the bottom left temperature there, it is going to be equal to P times V divided by NR. That's just rearranging PV equals nRT. And so getting the values from our graph, we have a pressure of 106 times 10 to the third, a volume of 1. We have 60 moles of gas, and R is 8.314. So I get a temperature at the first spot to be 212.5 Kelvin. Similar equation, what I'll call T2, which is at the end of process 1, is going to be the pressure, 212 times 10 to the third. Pressure is changing. The volume is remaining constant at 1, divided by 60 times 8.314. And this one gives us 425 Kelvin. Now what we're going to do with those is go back and put them into our delta T equation to find change in internal energy. And we'll get delta U equals 3/2 times our number of moles, which is 60, times R, which is 8.314, times your change in temperature, which is 425 minus 212.5. And we will get a change in internal energy, which remember is the same as Q, which is what we're trying to find, of 159 kilojoules. Now, this is only for process 1. For process 2, we're going to go about a similar type situation, but we've got to think for process 2, it is isobaric, so in this case the work doesn't equal 0. We're going to still have delta U equals W plus Q, and so Q is going to be equal to delta U minus W. So now what we have to do is almost a little bit more. We have to use the same method in order to find delta U, but then we have to additionally get the work. So first, delta U is going to be 3/2 times our number of moles times R times our change in temperature, and our final temperature in the top right corner of your graph is going to be 212, I'm just not going to write it down, times 10 to the third kilopascal, or 212 times 10 to the third pascals, times 3 is your volume, 3 meters cubed, divided by 60 times 8.314, and you should get, for that temperature, 1,275. And then we knew from above that our other temperature at the start of process 2 was 425 Kelvin. So I will subtract those, and you can get a delta U, which is 636 kilojoules. So I'm halfway there. I've got my delta U part. And in order to go ahead and find the work done, I'm going to calculate the area under process 2, which is just a rectangle. And so the area is going to be the base of the rectangle, which is 2, the volume, times the height, which is 212 times 10 to the third pascals. And I get a work of 424 kilojoules. Now, since process 2, the arrow is moving to the right and the volume is increasing, this actually becomes a negative. And so now, kind of putting it all together with the second law of thermodynamics, I have Q equals delta U, which is 636, plus my work, which is, delta U minus work, which is negative 424. And in the end, I will add them together, and I get a total Q of 10,060 kilojoules. Now, finally, if you wanted to find the total heat for the whole process 1 and 2, you would just add the 159 kilojoules from process 1 to the 10,060 kilojoules from process 2, and there you go. And I believe you get 12,019 kilojoules, which is Q total. Alright, so that was part A, as complicated as it was. Parts B and C are not as bad. Part B in number 40 wants to know how much work does the gas do during this expansion. And your total work is going to be the work from process 1 plus the work from process 2. Sorry about that. And we've already considered this. The total work, the work from process 1 is 0, and the work from process 2 was negative 424 kilojoules. So therefore, your total work is negative 424 kilojoules. And last one, part C, is asking what is the change in internal energy of the gas along process 1 and 2. And we know delta U is Q plus W. And so our change in internal energy is going to be our total Q, which is 1,219 kilojoules, plus our work, which is negative 424 kilojoules. So combining your two equations, or your two answers from above, and we get a total change in energy of 795 kilojoules. And that should be it for problems from chapter 18.